Dear students, now we will start assignment problems or assignment models, right? So in this class, we will study what an assignment problem is and how to obtain its optimal solution by Hungarian method or Hungarian algorithm. Assignment problem. Basically, assignment problem is a special case of transportation problem. In transportation problem, there are one-to-many allocations possible, but here in case of assignment problem, there is only one-to-one allocation is only possible. And in transportation problem, we have supplies and demands in different numbers, but in assignment problem, these will be treated as only one because one facility can be allocated only to one activity or project. Okay, so one-to-one allocations are possible in assignment problem. So here we treat all the supplies at different supply centers one, and all the demands as one. So assignment problem becomes a special case of transportation problem. Okay, so here let Xij denotes the assignment of facility I to job J such that Xij takes value or is equal to 0 if ith facility is not assigned to jth job, and its value is 1 if ith facility is assigned to job J. Okay, so these are the decision variables take only 0 and 1 values. When assignment is done, its value is 1, and not done, in that case Xij assumes 0 value. But in transportation problem, the Xij values are all greater than equal to 0 and anything else, right? So then the assignment model is given by minimize Z. Z means total cost of assignment. Okay, objective is to minimize that. To minimize Z is equal to J from 1 to n, I from 1 to n, Cij, Xij, right? To Cij, what is Cij? Cij is the cost of assigning ith resource to jth activity, right? And Xij I have explained earlier. It takes value 1 when ith resource is assigned to jth activity, and otherwise its value 0. Subject to the constraints. Likewise, transportation problem, summation j from 1 to n, Xij is equal to 1 for I equal to 1 to n. Here m and n are equal. Okay, number of rows and number of columns is equal. Okay, and in case not equal, we have to make equal. So this is 1, and again I from 1 to n, Xij is equal to 1. Okay, earlier in transportation problem, here it was ai and here it was bj, but now these values are only 1, right? So and Xij equal to 0 or 1. So now this is the mathematical formulation of assignment problem. Next is Hungarian algorithm. How Hungarian algorithm works. So I'm taking a very simple example, and this from taken from Operation Research by D.S. Hira, book by D.S. Hira. And this example is just like there's 1, 2, 3, 4 resources to be assigned to 4 jobs, or so 4 activities, 1, 2, 3, 4. Okay, and 15, 13, 14, etc. all these are the assignment costs. Okay, so this is our problem, and we have to optimize it. We have to find out the optimum cost of assignment. The next step is, okay, Hungarian algorithm or Hungarian method. Either proceed row wise or column wise. Okay, so here I am proceeding row wise. So what to do? Subtract the smallest element in each row from all elements in each row. Okay, suppose I am selecting the first row. So here minimum cost is 13. So subtract 13 from all other elements. 15 minus 13 2, 13 minus 13 0, 14 minus 14 13 1, and 17 minus 13 4. So I get 2014. Similar is the case with, let us take any other. Let us take the last one. So here 14 is minimum. 14 minus 14 0, 16 minus 14 2, 17 minus 14 3, and 15 minus 14 1. So 1302. You can see here 1302. So this table is made just by doing row operations, row reductions. So these values I obtain. Okay, I just discussed. What to do next time? If you have proceeded row wise first, then you have to proceed then column wise. And if you had proceeded column wise first, then we have to proceed row wise. So here we have proceeded row wise first. Now we have to proceed column wise, and we have to do the similar thing with all these columns. So select the lowest cost and subtract it from all other elements. So now the elements are like this. 0 is the minimum cost, so subtract 0 from all others. All the entries will remain the same. Here again 0 is the minimum, so all entries will remain the same. Then here again, and you see this fourth column. So here 1 is minimum, subtract this 1. So 4 minus 1 3, 2 minus 1 1, 1 minus 1 0, 2 minus 1 1. So now the entries will be like this: 3 1 0 1, and these will remain unchanged as in the previous table. Okay, after this, do the assignments. Okay, now how to do the assignments? The way is either proceed row wise or column wise. So if I proceed row wise, what to do? We have to find whether there is a single 0 in the row. Yes, it is available. So put this 0 inside a circle, showing that an assignment has been done in the cost effective cell. Okay, so if I put this 0, because this is only 1 0 available in the first row, and is put in this inside the square, and it means that an assignment has been done. What is that assignment? Means 1 has been assigned to 2. One resource has been assigned to the activity 2. Okay, so yes, and C in the column in which this row is 0 is lying, is there any other 0? If there are any other 0, then we have to cross them, because this 2 or this activity, this 2 some resource has been allocated to 2, and second times there should be no allocations to 2. Okay, so now coming to the second row, yes, there is a single 0. Put this inside the circle, and see in the particular column if there is any other 0. No 0, so nothing, no problem. Now go to the third row. In third row there are 2 zeros. Assignment is not possible. Go to the next row, that is fourth row. So here, yes, single 0 is here. Putting this 0 inside the square, and see in the particular column in which this 0 is lying, is there any 0? If it is, then cross that. So here it is, so I have to cross it. Then after that, proceed column wise. First row, this 0 is assigned. Second row, this 0 is assigned. Sorry, the second column, this 0 is assigned. Third, this 0 is assigned and this is crossed. And now go to the fourth one. Yes, in fourth column there is a single 0 put inside the square, and now all the assignments have been done, just like we can see. This I just told that if assignment is made in this row and then go to this column, any other 0, then put cross it. This is simply a cross, nothing else. And then when we did column wise, I found that in the fourth column there was a single 0 and I put it inside the square, showing that 4 assignments have been done. Okay, and these are unique assignments. That is, 1 is assigned to 2, 2 is assigned to 1, 3 is assigned to 4, 4 is assigned to 3. These are the optimal. Okay, so optimal assignments, and the corresponding total minimum cost is 49. Okay, how it is obtained? So I just added the costs available in these cells in the original table. Here the cost here, cost here, cost here, and cost here. Now let's go back to the original table. Here it is 13 plus 11 plus 12 plus 14, like this. So you can see 13, 11, 11, 14. Okay, adding all this giving me 49. So this is my answer. This is my total minimum assignment cost. Okay, now I am taking up one more example from the same book, example 4.6-2. 4 different jobs can be done on 4 different machines. The setup cost and takedown time costs are assumed to be prohibitively high for changeovers. The matrix below gives the cost in rupees of producing job I on machine J. Okay, so this is the cost structure. Yes, jobs and machines 5, 7, 11, 6. These are this is the cost structure. Okay, how should the jobs be assigned to various machines so that the total cost is minimized? Again, the similar kind of problem, and we will apply the Hungarian method to solve it. Okay, what are the steps? Yes, we proceeded row wise and we got these values. Minimum cost 5, 5 minus 5, 0, 7 minus 5, 2, 11 minus 5, 6, 6 minus 5, 1, 0 to 6, 1. Similarly, 3, 0, 4, 1. And all this row wise we have done these reductions. Now column wise, so 0 subtracted from all others, all elements will remain the same. Again 0 here, so this column will remain the same. Here 0, this column will remain the same. Only changes will be here. So 4 is minimum, so here 2, 0, 2, 1. 2, 0, 2, 1, and all other elements remaining the same. Now we have got a reduced matrix after row and column operations, and after that we do the assignments. Okay, so yes, in first row there is single 0, do the assignment. Second row no single 0. Third here, yes, it is a single 0, do the assignment. And then fourth row single 0, do the assignment. Then after that we proceed column wise, and we find that this and this, only 3 assignments are possible. So but for optimal solution we must have 4 assignments. That is, the solution is not optimal. If it's not optimal, what we do? We do like this. First of all, we find the minimum number of lines covering all the zeros in that reduced matrix. So mark this mark the rows for which assignment has not been done. Okay, let us go back. Rows for which the assignment has not been done. So this is the row, third row. There is no assignment, okay, no zero inside the square. So I have mark like this, tick mark, okay. Then the second step is mark columns not already marked which have zeros in marked rows. Marked rows and zeros which have zeros in marked rows. So this is a marked row, and in this row the zero is here. Okay, so now mark this column which corresponds to this. So I marked this like this. Okay, again this. Okay, but the next is mark rows not already marked which have assignment in marked column. Okay, so this is a marked column and here it is assignment. So mark that row also which has assignment in the marked column. So this is also marked. So now what are marked? This one, two rows and one column. Now what to do? Next step is, okay, repeat steps 2 to 3, this and this, until no more marking is possible. And after that, draw lines through all the unmarked rows and through all marked columns. Very important. So unmarked rows and marked columns. Go back. Unmarked rows. This is unmarked row and marked column. So, okay, I draw a line through unmarked row. From this row I cannot do, from this row I cannot do. It is also unmarked, so draw a line and through marked columns. So marked column is this one, so this. So I followed these steps to determine the minimum number of lines covering all the zeros. Okay, this is how these lines can be drawn. So remember these steps, 5 steps. Okay, very important. Okay, and what after that? Once we have done it, okay, now there are certain covered elements and certain uncovered elements in this matrix or table. What to do? Find out the minimum element among all these uncovered elements. So that minimum element is, see here, 2, 2, 1, 3, 2, 3. This is 1. Okay, this is 1. Now subtract it. 1 minus 1, 0, 2 minus 1, 1, 2 minus 1, 1, 3 minus 1, 2, 2 minus 1, 1, 3 minus 1, 2. So these are the new elements now. Okay, what after that? All the covered elements will remain unchanged and add this minimum element at the intersection. So this 0 will remain as it is. 3 plus 1, 4, because if this element is lying at the intersection, here this. And this 0 will remain the same, 1 will remain the same, 1 will remain the same, 0 will remain the same, but here it is intersection. 7 plus 1, 8. So I get a new table. You can see here 8, 4 and all this. This is a new assignment table now, resultant table after doing this transformation. Okay, now we have to see whether we have obtained the optimal solution or not. Again we have to cover, again we have to do the assignments likewise earlier, that is there any single 0 available in any row. So in first row, second row 2 0, third row, yes, not possible. Second row and third row 1 0, yes, 0 is here. And if there is any other 0 in the same, in the column corresponding to this 0, then cross that. So if I put this inside square, if I do the assignment, I have to cross this 0. and then go to the fourth row. Yes, single zero, put this inside the circle, do the assignment, and then cross the zero in the particular column. And then we proceed column wise and do the same thing. We get this one. Okay, we find that this zero, and this zero, three zeros are assigned. This three assignments are made, but still we need one more assignment. Again, we have to cover all the zeros in this table by the minimum number of lines, and we follow this procedure given here again on page this slide number 13, and we find that okay, this is marked row, and these two are marked columns. So what to do now? Draw the lines. Okay, if we draw the lines and do the same procedure, okay, what we get, cover the lines, yes, and if we do the procedure, then this will be 0, okay, and what will be the cover lines? Minimum number of lines. What was the rule? That step is now taken up. You can see yes, where was 13, yes. Draw the lines through all unmarked rows and marked columns. So see here, unmarked row, this only one, and then marked columns. One line will be like this, so like this, one line will be through this, and one line through this, and one line through this. So there will be three lines. Yes, covering all the zeros. And after that, what we do, we find the uncovered elements and covered elements, and subtract, find out the minimum element from among the uncovered ones, and that is 1, subtracting 1 from all those and adding this 1 at intersection. And after that we find out this is the situation: 0, 0, 0, 0 in the first row, and 5, 0, 0, 2, 0, 1, 0, 2, 8, 0, 0, 0. So this is the situation now. Okay, now how to do the assignments after this? Here if we see that okay, no single zero possible in the first row, no single zero in the second because 2 zeros, no single zero in the third row, no single zero in the 3 zeros, no single zero in the fourth row. Now column wise, 2 zeros, second column 2 zeros, 3 zeros even, third 3 zeros, 4 zeros, fourth column 2 zeros. So no single zero is possible in any case. In this case, when this kind of situation happens, what you have to do, arbitrarily you have to assign, do the assignment, okay, in any of these rows and columns. So, and yes, I may have given some note. Yes, there's a note. If a single zero is not possible for assignment in any row or column, we make assignment arbitrarily in any row and cross the remaining zeros in the same column as well in the same row. So if I do this arbitrary assignment here, then cross all the zeros in the column and the row and column to which this zero corresponds to. So these are crossed, and this zero is also crossed. Okay, now what after that? Go to the second row, no single zero possible. Okay, now go to the third row, no single zero possible. Sorry, third row, yes, third zero, single zero is possible. Second row, no single zero possible. third row single zero possible because it's crossed, and it is here 1, and then cross all other zeros in the column. This zero is crossed and this zero is crossed, and this is already crossed. So go to the next. So yes, here was this crossed earlier? No, it was not crossed. If you move here, this is crossed, and this was not crossed, and this was not crossed. Okay, now proceed column wise. So this is what was done. This was done crossed here earlier, and here if you see in this column, if you see, yeah, it is crossed now. Okay, so this is single zero now, because if I have done this no, column wise, yes. So if we see this fourth column, okay, first if I see this in this column, this is single zero, it is done, and these rows are crossed. So if I do this, then I go to the second column. If I go to this column, this single zero is there, I can put it inside, and then after that, if I put this inside, then this row corresponding other zeros in the row will be crossed. So now I have only single zero in the third row, third column. Okay, and it can be put inside the square. That is, assignment can be done. So this is how these 4 different unique assignments are possible at this stage. And this is J1 to M1, J2 to M2, J3 to M3, and J4 to M4. So these are the optimal assignments which are possible, and hence it's the optimal solution, and we can find out optimal assignment cost. That is, costs, we can add the costs at this point, this, and this. So that is, if I go back to the same table, we can see that 5 plus 5, 10, 10 plus 10, 20, and 23 is the minimum value of Z, minimum objective function. Okay, so this is how this problem is solved. Thank you very much.